Well, I've checked, and this is the last page of making redox tables. So if you can hang on through two more without losing your mind, you will have made it. So you probably know the procedure by now. Each of these reactions proposes that two chemical species meet, and one of them tries to take electrons from the other, and either they succeed and we get a reaction, or they fail and we don't, and there isn't one. Now, the wrinkle in these new questions is I've been saying up till now that it's usually the more positive species taking electrons from the more negative one, and I think that's usually valid. But look what happens in this first question. X2 plus is trying to turn into X4 plus. It's trying to become more positive. You don't do that by gaining electrons. You do that by losing electrons. It's Y here who is trying to go from Y2 to Y with a negative charge. So the story in this first reaction is Y is trying to take electrons from X, and apparently they succeed in doing that. So our table starts off with, or our ranked list anyway, starts with Y being stronger than X. So overwhelmingly often it's the more positive thing taking the electrons, but do watch out for this. If you see the charges going not the way you expect, it's time to lean forward and look a little more carefully. Second reaction, we have a similar thing happens here, actually. Q starts with a -2 charge and then goes to -4. So even though this thing is already negative, it somehow attracts more electrons and becomes more negatively charged. Seems unlikely to me, but all right. The fact that this reaction happens tells us that Q is better at taking electrons than P is. Q is higher than P. Another thing this question is doing to us is we have a hierarchy with Y and X here and a totally separate one with Q and P, and we don't know how these are connected yet. So just be patient. Hopefully that'll become clear as we go on. Next one. Here we have P, 3 plus, turning into atomic peace, so that's gaining electrons, and Y minus going up. So yeah, this one is the p ion taking electrons from Y, and it succeeds in doing that, so that tells us P is higher than Y. And that tells us how these lists are arranged. We have Q is higher than P is higher than Y, and we already know Y is higher than X. So there's our merged list that has all the things in it so far. And one more reaction here. X4 plus turns into X2 plus. So X4 plus is trying to gain electrons here and take them away from V, and it succeeds in doing that. So X is even higher than V. So there they are in order. And if we make a redox table out of that, because these are made up elements, I'm going to have to look at the charges that they've provided. Okay, so we want, in all of these cases, the more positive thing gains electrons, turns into the more negative thing. That's how our data book is laid out. So we're going to have Q2 minus picks up 2 more electrons and turns into Q4 minus. After that, we have the P row, which is P3 plus turning into P. The Y row is diatomic Y, so Y is something like nitrogen or oxygen, it only forms -1 ions, so it's better to think of it as something like fluorine or chlorine. Here we could say Y2 picks up 2 electrons and turns into 2 Y minus ions. Our X row is this, it's going between +4 and +2 charge. So we start with the higher charge. Then it gains some electrons, and those drag down the charge to a mere 2 plus. This would be something, this is what tin does. Tin and lead have +4 ions and then gain electrons and can turn into +2 ions. And our bottommost thing is V, which forms a weird triatomic that you don't see real often. And this is turning into V2 minus. And if this is going to be balanced properly, we'd have to have 3 V minuses, and that would mean there's a total of 6 electrons involved. Is it important to get those numbers right? No. All we really care about is the order of our redox table, but if you wanted to really nail this, you would think about these details. And now that we have this done, our strongest oxidizer is just the top left thing, the Q2 minus ion, and our strongest reducer would be the bottom right thing, the V2 minus ion. Okay, and our last one will be with real elements, apparently. You remember we've had questions where we had ions reacting with metals, and in most of those we would present the information in a table, and we'd say there's a reaction or no reaction, so on like that. Here they're doing it with a bunch of English sentences, so let's see if we can translate this into a redox table. Beryllium metal is some kind of reducing agent. But how strong is it? It reacts with cadmium and vanadium, but not with radium. What would it look like? Imagine this is the page in our data book. If beryllium metal reacts with a cadmium ion, where is that cadmium ion? Would it be down there, or would it be up here, or would it be dead even, or what? Spontaneous reactions have to go that way, which means the cadmium ion must be higher than beryllium is. And vanadium must be higher as well. Unfortunately, we don't know the order of them, so up here we're going to have, for the moment, cadmium and vanadium and order to be determined. I'll put them on the same line for now, and we'll shuffle that shortly. And they say beryllium does not react with radium, so the radium ion must be lower down, something like that. Okay, so we get all that from the first sentence. Beryllium is lower than cadmium, but it's higher, lower than cadmium and vanadium, but it's higher than radium. That takes care of this first line. Cadmium metal does not react with any ions. That means cadmium metal must be higher than all of these things, so that all the lines are uphill, all of them are non-spontaneous. So from that we get cadmium's got to be even higher than vanadium is. V2 plus, we'd have V over here. Beryllium looks like that, and we'd have radium metal like so. So, beryllium reacts with cadmium, yep, it should. Beryllium reacts with vanadium, yep. Beryllium does not react with radium, that would make sense because this line's uphill. Cadmium doesn't react with anything, yep, because all these ions are below cadmium. You get non-spontaneous reactions with all of them. Radium metal reacts with beryllium, yep. Cadmium, yep. And vanadium, yep. And the vanadium ion reacts only with a cadmium solution. All of that makes sense with the order we have here. So, I never liked remembering them this way because you can't just think like cadmium is higher if it doesn't react. You have to be clear about whether it's the cadmium ion or the cadmium metal you're talking about. Ions that are really high react with lots of stuff. Metals that are really high react with hardly anything. So you can remember both of those facts if you want to. I never found that was a really graceful way to keep this stuff in my head. But if it works for you, terrific. So now that we have this all organized, SOA is the top left corner, the cadmium ion, and SRA is the bottom right corner, radium metal.